Hello student, today I am going to explain you how to find out the loss of kinetic energy due to collision for the case of oblique impact. Now let us consider these two spheres of masses m1 and m2. Now let the velocity of this first sphere be u1 making an angle alpha 1 with respect to the line of centers before impact, and v1 be its velocity after impact making an angle beta 1 with respect to the line of centers. C1, C2 is a line of centers. Similarly, for the second sphere, let us take u2 to be the velocity of the second sphere before impact making an angle alpha 2 with respect to the line of centers, and after impact let its velocity be v2 making angle beta 2 with respect to the line of centers. Now the component velocity of the first sphere before impact will be along the line of centers, it will be u1 cos alpha 1. Perpendicular to the line of centers, it will be u1 sin alpha 1. Similarly, after impact, the component velocity of the first sphere will be v1 cos beta 1 along the line of centers, and perpendicular to the line of centers will be v1 sin beta 1. Now for the second sphere also, the component velocity along the line of centers will be u2 cos alpha 2, and u2 sin alpha 2 will be the component velocity perpendicular to the line of centers. Now after impact also, the component velocity along the line of centers will be v2 cos beta 2, and perpendicular to it will be v2 sin beta 2. Now let us find out what will be the loss of kinetic energy. Now we know that for the collision of smooth spheres, the action and reaction will take place only along the line of centers. That means along the line C1, C2. Perpendicular to the line of centers, there will be no change in their velocities. That means the component velocities before impact and after impact in the direction perpendicular to the line of centers will remain the same for the first sphere and for the second sphere. So it means that v1 sin beta 1 will be equal to u1 sin alpha 1. We can name it as equation 1. Next, this one also, v2 sin beta 2 will be equal to u2 sin alpha 2. This is equation 2. Now by conservation of momentum, what is the total momentum before impact? It will be m1, that is along the line of centers. So it will be m1 v1 cos beta 1 plus m2 v2 cos beta 2. This will be equal to the total momentum before impact, that is m1 u1 cos alpha 1 plus m2 u2 cos alpha 2. Name this as equation 3. And by Newton's experimental law, we have this relation v2, the component velocity along the line of centers. So it will be v2 cos beta 2 minus v1 cos beta 1. This is called E times of the component velocity, the relative velocity of approach before impact, and that one will be u1 cos alpha 1 minus u2 cos alpha 2. So name this as equation 3. So we have to use this 4 equation now. This is equation 4 in order to find out what will be the loss of kinetic energy due to the collision for the case of oblique impact. Now we know by the formula what is the loss of kinetic energy. It will be half of mass into the square of its velocity. Now we have this one. For the first sphere, the velocity will be this one, u1 cos alpha 1 along the line of centers, and perpendicular to it, it will be u1 sin alpha 1. Similarly, for the second sphere, it will be u2 cos alpha 2 along the line of centers, and u2 sin alpha 2 will be the velocity perpendicular to the line of centers, that is before impact. So in that case, we'll have this one. Loss of kinetic energy will be half m1 into u1 cos alpha 1 the whole square plus u1 sin alpha 1 the whole square plus half of m2 u2 cos alpha 2 the whole square plus u2 sin alpha 2 the whole square minus the kinetic energy of the second sphere. The kinetic energy of the second sphere will be, after impact will be this one. It will be minus half of m1 into v1 cos beta 1 the whole square plus v1 sin beta 1 the whole square plus half of m2 into v2 cos beta 2 the whole square plus v2 sin beta 2 the whole square. But now for this one, what is v2 sin beta 2? v2 sine beta 2 can be replaced by u2 sine alpha 2. So it comes out to be half m1 into u1 square cos square alpha 1 plus u1 square sine square alpha 1 will remain there. Then plus half m2 into u2 square cos square alpha 2 plus u2 square sine square alpha 2 minus half of m1, this will remain as it is, v1 square cos square beta plus, now v1 sine beta 1. What is v1 sine beta 1? From equation 1, it is u1 sine alpha 1. So you can replace that one by u1 sine alpha, u1 square sine square alpha. Then next will be plus half m2, then v2 square cos square beta 2 will remain as it is. But for this v2 sine beta 2, you have to replace it from equation 2. We have it as u2 sine alpha 2. So it will become u2 square sine square alpha 2. Now you can see from here I have half m1 u1 square sine square alpha 1, and here I have it as minus half m1 into u1 square sine alpha 1 square. So this one can be cancelled. That means this term and this one can be cancelled. Now from the second one I have u2 square sine square alpha 2, and from the fourth one I have this one. It is minus half m2 into u2 square sine square alpha 2. So this will be cancelled with half m2 u2 square sine square alpha 2. So this and this one will be cancelled. So the remaining term now in this case will be equal to half m1 into u1 square cos square alpha 1 minus, let us take the multiple of m1. So it will be v1 square cos square beta 1 plus half m2 u2 square cos square alpha 2 minus v2 square cos square beta 2. So finally we have this one. The loss of kinetic energy is equal to this. Now let us multiply and divide by the sum m1 plus m2. So it will become m1 plus m2 by 2 times of m1 plus m2 into m1. So the same thing will be here inside the bracket. It will be this one plus half again for the second term also. You multiply and divide by this one m1 plus m2. We need to simplify this one to get the final loss of kinetic energy. 2 square cos square alpha 2 minus v2 square cos square beta 2. That is by multiplying and then dividing by this one. Now let us take this one m1. Okay, I'll take half of m1 plus m2 as a common factor. Now here you multiply m1 plus m2 m1 into this term inside the bracket. Similarly for the second one also, you bring this m1 plus m2 into m2 inside this one. Then you'll see that you'll get this term m1 square u1 square cos square alpha 1 plus m2 square m2 m1 u1 square cos square alpha 1 minus m1 square v2 square cos square beta 1 minus m1 m2 v2 square cos square beta 1, then plus m1 m2 u2 square cos square alpha 2 plus m2 square u2 square cos square alpha 2 minus m1 m2 v2 square cos square beta 2 minus m2 square v2 square cos square beta 2. So these are the terms after multiplying this one m1 plus m2 m1 into the first term and m1 plus m2 into m2 into the second term. So after expanding this one, so finally you'll see that you can express this one as half of m1 plus m2 into, now it will give you can rearrange this term, so you'll get m1 u1 cos alpha 1 plus m2 u2 the whole square you'll get plus m1 m2 into u1 cos alpha 1 minus u2 cos alpha 2 the whole square minus m1 v1 cos beta 1 plus m2 v2 cos beta 2 the whole square minus the last term will be m1 m2 v2 cos beta 2 minus v1 cos beta 1 the whole square. But this one, after simplifying, rearranging this term, then you'll have this relation. Now, what is m1 v1 cos beta 1 plus m2 v2 cos beta 2? So that one, by principle of conservation of momentum from equation 3, it is m1 u1 cos alpha 1 plus m2 u2 cos alpha 2. So this is equal to half of m1 plus m2. The first term will remain as it is, m1 u1 cos alpha 1 plus m2 u2 cos, this is cos alpha 2 the whole square, then plus m1 m2, this will also remain as u1 cos alpha 1 minus u2 cos alpha 2 the whole square, then minus, now in place of that third term you replace it by minus m1 u1 cos alpha 1 plus m2 u2 cos alpha 2 the whole square from equation 3, minus the last term, it is m1 m2. Again, the last term v2 cos beta 2 minus v1 cos beta 1. From equation 4, it is e times of u1 cos alpha 1 minus u2 cos alpha 2. So you replace this one by this term, so it will become e into u1 minus u2 cos alpha 2 the whole square. So on simplifying this one, you'll get finally half of m1 plus m2. You expand this one and you'll see that some terms will be common. Now from here you'll see that m1 m2 will be common because some terms will be cancelled. So then you'll get here m1 m2 will be a common factor, and then inside the bracket it will remain as u1 cos alpha 1 minus u2 cos alpha 2 the whole square minus e square u1 cos alpha 1 minus u2 cos alpha 2 the whole square. You can see from here that the first term, this one, m1 u1 cos alpha 1 plus m2 u2 cos alpha 2 the whole square, but I have minus here m1 u1 cos alpha 1 plus m2 u2 cos alpha 2. So this one and this will be cancelled. So only the second term and the fourth term will remain there, where m1 m2 is a common factor. So finally, this one gives you the loss of kinetic energy, half of m1 plus m2 into m1 plus m1 m2 into, okay, this one, loss of kinetic energy now finally can be simplified as m1 m2 divided by 2 into m1 plus m2 into 1 minus e square into u1 cos alpha 1 minus u2 cos alpha 2 the whole square. So this is the loss of kinetic energy for the due to collision for the case of oblique impact. It is m1 m2 by twice of m1 plus m2 into 1 minus e square into u1 cos alpha 1 minus u2 cos alpha 2 the whole square.